The second comparison test that I want to talk about is referred to as the limit comparison test. So once again, we are going to be comparing two series. And for complete lack of creativity, let's refer to them as the sum of a sub n and the sum of b sub n. We are, however, going to remove the stipulation that one of these is greater than the other. If you can show that the limit as n approaches infinity of the ratio of the terms of these two series is equal to c, where c is finite, that is, not infinity, and non-zero, then both series converge, or both series diverge. The idea is, if this limit exists, that means that essentially both of the series are getting larger or smaller at the same rate. Now, if they're getting larger or smaller at the same rate, then that means that they will have the same level of convergence. They will either both converge or they will both diverge. So in the last video, we were comparing the sum from n equals 2 to infinity of 1 over n squared and the sum from n equals 2 to infinity of 1 over n squared minus 1. We attempted to use the direct comparison test, but the inequality was facing the wrong way for us to draw a conclusion. So what we're going to try is the limit comparison test. Now, for the record, as we're trying the limit comparison test, I am aware that this series converges due to the p-series test. Now, if we can prove that this limit up here exists, then we'll be able to show that this converges as well. So with that in mind, we're going to take the limit as n goes to infinity of the ratio of these two terms. It does not matter which one goes on top and which one goes on bottom. The reason it doesn't matter is if this ratio is finite and non-zero, then the reciprocal of it will be finite and non-zero as well. Now, technically, this takes the form 0 over 0, so we could perform L'Hopital's rule. Instead, what I see here is a single fraction divided by a single fraction, so I'm going to change it to be multiplying by the reciprocal. This will be the limit as n goes to infinity of n squared minus 1 over n squared. I'm going to distribute that n squared to both of the terms in the numerator, and we will get 1 minus 1 over n squared. Now, we can't really plug in infinity, but if we allow n to go to infinity, then 1 over n squared will go to 0. The result that we get is 1, which is finite and non-zero. As soon as you get that the limit is finite and non-zero, you are able to draw a conclusion. Because the series that we compared it to converges, this one will converge as well. Therefore, by the limit comparison test, the series from n equals 2 to infinity of 1 over n squared minus 1 converges. Try to keep that nice and uniform as far as final answers are concerned.